So let me say something about the homework. And this is kind of, I guess I've decided. I'm probably just gonna let you guys work on this homework. This is kind of a get your hands dirty, so I recommend you all get together. I mean, there's nothing better than roll out before fall break. So talk about this. It actually is homework, so we've got to correct that. This is kind of tying together some stuff that I promised you all earlier. So first little definition. If you have an integral domain quotient field K, and omega is some element of this quotient field, we say that omega is almost integral over R. If there is a non-zero, I guess that's important, element such that R blasts every power of omega back down into R, right? The collection of all almost integral elements over R is denoted by R prime, and it's called the complete integral closure of R. The name's something of a misnomer because it's going to turn out, we're going to see later, that the integral closure is always integrally closed, but the complete integral closure need not be completely integrally closed. So sometimes you can keep priming things, and in fact, you can go on forever, which really is, somebody named that a little bit prematurely, I think. Number one, show the complete integral closure of R is an overring of R. That's obvious enough because it's all from K. That contains the integral closure. So in particular, every element that's integral is almost integral. They named that one right. Number two, let R be a UFD with quotient field K. This looks like I'm doing two different things, but there's actually a method to this madness that goes all the way down here. Show that R of X is a UFD. There's a number of ways you can do this. I like to do it using the fact that to show Rx as a UFD, show every non-zero prime ideal contains a non-zero prime element. I think that shortcuts it a little bit. And the technique of this will probably give you an idea about how to do the second one. And this one actually connects to the next problem. Show if you have, again, R is UFD, show if f of x in Rx is monic. And suppose that f of x factors, right? With both of these factors in Kx, one stipulation that one of the factors is monic. Then, and I've worded this wrong, I'll fix this. Then both m of x and k of x, this is correct. They are both monic, it turns out. But in fact, m of x and k of x are actually both in R of x. That's what I meant to say there. So this, I'll fix that, both in Rx. And you actually use this here. Let D be a square free integer. Show that the integral closure of Z and Q radical D is given by this. I've already given you this before. And showing this, these elements are all integral, that should be pretty straightforward. That you should have no problem with that, finding the polynomials. The other way, that is showing that this is exhaustive, right? This is all the integral elements, might depend on this one a little bit, right? And this is a kind of something that I brought up before. Suppose that you have an element of this integral closure, right? What is it? It has to be a root of a monic polynomial of coefficients in Z. Now I know it's the root of some polynomial with coefficients in Q of degree 2 or less, right? But it occurs to me that you might have some element that's integral that is a root of some degree 2 polynomial with rational coefficients. But it's also a root of a monic polynomial, say of degree 5, and that's as small as it can go. This problem might help you show that this can't happen. All right. And finally, number 5, this is really getting the dirt on your hands here. For the ring of integers for the field Q adjoining with the square root of -15, describe the behavior of the rational primes P completely. That is the behavior, how they behave upstairs in the ring, right? I want to know, does it remain prime in this ring of integers? And if it doesn't remain prime, tell me, does it ramify? Does it split into a square of something? Does it break down into two irreducible prime factors? You should be able to sort of tell her, and you also should be able to tell me if it's UFD or not. That'll probably come up, although I didn't ask you that question, it'll probably come up in a problem. Okay, any questions on that? I will be out of town tomorrow, as will some of you in here as well. So those of you that are here, I encourage you to work on this and have fun and, you know, thank me for a glorious weekend. Okay, any questions?
What is the correct due date on that?
Not that. I don't know yet, like a couple of weeks. Yeah, you know, you guys know what a stickler I've been for your deadlines, right? I'll figure out, it'll be a couple of weeks, right, certainly. Comfortably after the break. I'm integrating your second homework too, so I hope to get done with that. Ironically, I might have some time over the weekend to do it, so. Okay, other questions? Okay, so last time I beat you all to death with a bunch of advanced valuation domains. They get more exotic. I mean, you can actually, the first time I ever saw it, right, you got a pair of elements that are non-zero, one of them divides the other. It's like, this is almost a field, right? But in fact, they exist in all dimensions. They can be infinite dimensional, they can be infinite dimensional badly. They can be so big that if you have any prime ideal that's not zero, then there's another prime ideal between it and zero. So they can be extremely large. Here are some properties of valuation domains, and I'll talk briefly about this. These are not characterizations, these are just properties that they have. If is a valuation domain, then B has solid property. Let's see, what are my favorites here? Number one. Stop here. Number one, V is quasi-local. That's kind of a neat thing. So any valuation domain has one and only one maximal ideal. B is integrally closed. That is to say, every element of the quotient field that is root of a mnemonic polynomial with coefficients B is already in B. Right? With respect to the problem set that I just showed you, B is almost never completely integrally closed. In fact, if you can stack, you've always got the zero ideal prime. If you have more than one non-zero prime ideal, it's not completely integrally closed. 3, every overing a valuation domain is a valuation domain. This actually shows that valuation domains are a strong property. So if you have any ring that is between B and its quotient field, it's still valuation domain. This doesn't happen for most kinds of rings that you think about. This is certainly not true for UFDs. It's not true for Noetherian rings in general. It is true for valuation domains. It's true for PIDs and it's true for domains, which I haven't defined yet. But we will get to. 4. Here's another one that's not true for most kinds of domains. Every overing of V is a localization. This is almost never true for other kinds of domains. It is true for PIDs, but even two-dimensional UFDs, if you look at a polynomial ring over a field in 2 variables, this is contained in F, X, Y, Y over X, Y over X squared, forever and ever. In fact, you could even stop at some point. This is an overring, it's not a localization. So this almost never happens. Number 5, every finitely generated ideal of B is, anybody want to guess this one? I'm gonna wait, it's the principle thing. There we go. Let's spell it. There we go.
All valuation means a big two.
What's that?
All valuation means a big two.
That is correct. That's exactly right. That's an astute observation. So in particular corollary, we'll call this Rodrigo's corollary. Every valuation domain is Bayesian. And guess what? Also quasi-local. So every valuation domain is Bayesian quasi-local. And in fact, that characterizes valuation domains. And I'll get to that in a moment. All I put prime in there for emphasis. In fact, in evaluation domain, all the ideals are linearly ordered. It's like a file cabinet. They're just all in order, right? This, of course, almost never happens in most interval domains you think of, right? Look at the integers, the ideals generated by 2 and 3 aren't even comparable, right? So these are some sweet properties, I'm telling you. And if I is an ideal of B, and let me say proper, then radical I. Okay, so let's think about this. So this will be sort of my proof for number 7. So we know what the radical is, right? It's the collection of everything X and V such that X to the N is in I, right? That's the definition of the radical, right? But does anybody know a fancy pants way of characterizing the radical? The intersection of all the primes, right? So if you take the intersection of all the prime ideals containing I, and all the prime ideals are linearly ordered, what happens with? So all the primes containing I are a chain. And what do we know from intersecting a chain of primes? It's prime. How about that? So there was some usefulness that came out of that homework problem set, right? Let me just talk through this now. If you believe the prime ideals are linearly ordered, I can rip off a whole bunch of this, right? So 5 and 6, I'm gonna maybe come back to. We've talked our way through 7. Well, why is it quasi-local? Well, I know that V has a maximal ideal because any commutative root of identity has a maximal ideal. If there's another one called N, they're linearly ordered, right? So M and N have to be the same. So there's only one maximal ideal. I'll come back here and close. Every overring of evaluation domain is valuable. How would we prove that?
Have the characterization that every element of the quotient field, either U or U inverses.
Oh, there you go. That's the slickest way to do it. So, number 3, for example, if V is contained in T in the quotient field, fine. Let omega be in K, then if I claim omega or omega inverse is in T, And that's all we need for valuation domain. Well, that's true of V, so it must be true of T. Because either omega or omega inverse is in V. If omega is in V, then it's in T and you're done. And if omega is not in V, then omega inverse is in V, in which case it's in T, right? So from that perspective, this is pretty easy to see, right? Number 4. Any ideas how we get this? So my claim is every overring is a localization. So suppose again, we have B. Some domain that contains our evaluation. What we have to do is we have to realize V as, I'm sorry, we have to realize T as V localized at some prime in V. So the big thing is how do we play Dick Tracy and find what the appropriate prime ideal is?
T minus V. Yeah, swell, so that's gonna be a close, and so you swell that to a prime. And V.
Use evaluation domain, so it's semi-local. So that's the.
Okay. T is a valuation domain,
Positive.
with maximal ideal. Call it in. Alright. Because we already know, as you point out, we know from 3 that it's valuation domain and it's quasi-local, it's valuation domain. Now, let P equal N intersect V. Now show P is V with plus T. Alright, do that as an exercise, it's pretty straightforward. Why interpret close? This was actually important. Valuation, and it's going to be important in a moment because valuation domains are always interpret closed. And as I sort of, did a little bit of a spoiler, valuation domains are actually intimately related to the interval closure of a domain. So what about, whatever that is, number 2?
There's a characterization, they said, in the recorded lecture, like U in the quotient field is integral over R if and only if U inverse is in R of U, but we know that one of them is in R.
Right. So my old Max Headroom classroom, as he said, U then U is integral over V if and only if U is contained in V U inverse. I think I did U inverse integral if and only if U inverse is in V U, but it's equivalent. Right? Okay, so all right, so how does this help?
Well, if U is already in B, then we're done.
Right,
If
so let me record that. I'm a slow fellow. If U is in B, then done, right? If not,
inverse is a B, so B joining U inverse is just B.
then U inverse is in B. So what does this mean?
B is going with U inverse is just B.
Well, so U is an integral, so U is integral. U is in VU inverse, right? But VU inverse is V. Because U inverse is already there. Right, and so in either case, U is in V and we're done. Everybody okay with that? How is every finally generated ideal is principle? I mean, this one's by induction, right? Everybody agree with that? Because it's clearly true if it's singly generated. If it's two generated, it's generated by A and B, and either A divides B or B divides A, whichever one divides it goes in. And then assume that if you have N generated, it's principal. Now look at N plus one generators, right? The N part is generated by a single element, and then the extra part is see which one divides the other, right? Finally, how about this one? I want to hit this one up. Why are the ideals linearly ordered? Let's do that. No more black here. Why are the ideals linearly ordered? This is an important. I'm gonna get contradiction from this, suppose not. Then, there exists I, J, and B with, I not in J and J not in I. So in other words, they're in common. This means we can select an X that's in I, but not in J. We can select a Y that's in J, not in I. So, everybody on board so far? But this is valuation domain. Right, so one of these has to divide the other. And of course, these are both non-zero since X is not in J and Y is not in I, it can't be zero. Without loss of generality, let's say that X divides Y. And what's the problem with that?
Why are things what they're saying?
So Y is X alpha, but X is in I. And so Y is in I, which is a contradiction. So the ideals have to be linearly ordered. Okay. Questions on that? Okay, I'm having a bit of a stroke here. Let me record this theorem. Let me ask you all. This is so familiar to me. I'm gonna need this, so whether I prove it or not, I can prove it pretty easy, but I think I already did prove this, or am I thinking of another semester? Theorem 7.4. We're gonna need this in kind of a build up to where we're going. Let R and T be rings. Let's see domains. Specialize this. I should have domains. U and the units of T. So U is some unit upstairs, and I, a proper ideal of R. then I survives. And either are you or are you inverse? And let me tell you what I mean, just to be clear, what do I mean survives? This means okay, so here's R, it's the little one inside of T. U is also in T, so these are intermediate rings, right? This is the smallest ring that contains R and U. This is the smallest ring that contains R and U inverse, right? What do I mean by it survives? It means that when you look at the ideal generated in RU by I, so just take a shovel and take everything in I and dump it into RU and see the ideal it generates. Then this means RU is strictly contained in RU. Or RU inverse is strictly contained in RU inverse. This is what it means to survive. It means that it's still a proper ideal. Right? Let me give you kind of a non-example. Well, this example has both positives and negatives to it. Look at C contained inside Z localized at the ideal generated by 2, and let me remind you, this is A over B. B is odd. So these are all rational numbers that I can express as an odd denominator. All right. If you look at 2Z in Z survives in Z localized to 2. Because the ideal generated by the even integers up here does not have, generates a proper ideal, like there's, because what you have is, what that'll generate up here is everything with an even numerator, right? None of which is invertible. On the other hand, 3Z, or in fact, any odd Z, does not survive in Z. Because 3 would have to be in this ideal that you're generating, right? And if 3's in there, and since 1/3 is in the ring, you get 1 is in that ideal as well, right? Because 3Z up here, there'll be a 3 in that set used to generate 3 times 1/3 is 1, and so you get the whole thing. Everybody okay, good. Another way to look at that is 3 as a unit up there. Everybody see what I mean by survives? It either stays proper or it blows up to the entire ring. I haven't proved this, have I? Have I done so? Okay. I know I've done it sometime in the past. Probably pretty recently. I don't know about you all, but this is the statement of it on the surface is not clear, I don't think. Suppose not. So let's prove that my proper ideal must stay alive in one of these extensions. If not, then we have a couple of equations that must occur. Then we must have Local Gina out there. And B0 plus B1 U inverse plus B2 U minus 2 plus BM U minus N equal 1 for AI, BJ, and I. Because what is a typical element? This first one is for the blowing up in RU. What does a typical element in IRU look like? Well, it's sort of like a polynomial with coefficients in the ideal I and powers of U. And hence this equation, right? A typical element of the smallest ideal containing I and U up there is this, or not necessarily containing U. In the ring, U adjoin. Everybody okay with that? And at the same time, if it blows up here, it's the same thing with my powers of U being negative, or well, non-positive, I should say. Okay. So here we assume
Just to clarify, so when you have I R of U, so that will be equivalent to I bracket U, is that correct?
yeah,
Is that what
yeah,
you're
in this
assuming
particular
for
case,
here?
yeah. Here we're going to assume that N is greater than or equal to M. And is as small as possible. Because, for example, if M is the bigger one, I'll just reverse the roles of U and U inverse because this is symmetric, right? So I'm going to assume that N is greater than or equal to M and that among all setups like that with N greater than or equal to M, N is chosen as small as possible. And what I'm going to do is contradict the minimality of N. So the strategy is I'm going to somehow build a smaller relation that involves less than N elements that gives you that. So how do we do this? Well, I mean, really, I'm going to look at this again and play it out, but it's really just high school algebra. So let's multiply second equation by U to the N. So I'm going to multiply by U again. And bring things over and rearrange this a little bit. I get, and let me justify this, 1 minus B0 times U to the N is equal to B1 Okay. So what did I do? I multiply this by U to the N and I get 2 U to the N terms, right? I get B0 times this, 1 times this. So I'll bring this over. So I have 1 minus B0 times U to the N. And then I'm left with this bit right here. Just multiply by U to the N. So got that. And now I'm going to multiply the first equation by 1 minus B0. I don't want to show all that stuff in there. So what am I gonna get here? I'm gonna get, so let's, multiply the first equation by one minus zero. Oh, you're right. So I'm gonna get one minus B zero. Do this the way I wanna do this. Times A zero. Plus A one U. Plus A n minus one U n minus one. Plus A n. One minus B zero, U to the n. Equals one minus B zero. So I just kind of spread things out for the, the dramatic effect here. Fine. Now notice. I can take this suitcase full of joy here and dump it into here, right? And what am I gonna get? I'm gonna get one minus B zero times A zero plus A one U plus A n minus one U n minus one plus A n times this mess. Right? Plus B zero is equal to one. How about that? So now I have an equation and it is a huge mess, but notice that none of the powers of U exceed n minus one. So I have, this contradicts minimality. So that establishes the lemma, and this will, or the theorem here, and this will be important because this is going to crop up very soon. Okay, any questions on this? Okay, keep this in mind. This is a linchpin right here. Theorem. Let R be the domain and with quotient field K. And I proper ideal of R. Okay, so we've got this proper ideal inside of it. Then there exists a valuation domain. That valuation overring of R. That is to say, R the K such that I survives in B. That is to say that IV is not in B. Okay, so we're up in the voltage here. This is a cool result because take any integral domain quotient field K and take any non-zero, any proper ideal. Then there's a valuation domain where that ideal survives. You often have to go up very far to the evaluation domain. You think, well, if I get closer and closer to the quotient field to get evaluation domain, I might be forced to kill this ideal I. Nope. This ideal, there's some way to do it where the ideal survives. All right. Here's a couple of extreme examples. If you take the zero ideal, just take the valuation domain to the quotient field. No problem there, right? But if you look in the integers, right, you have to go a long way to your valuation domains here because the integers are very much got ideals spread all over the place that don't compare. If you look at the ideal generated by 2, the valuation domain you could pick be Z localized at 2. If you look at the ideal generated by 5, Z localized at 5. If you look at the ideal generated by 30, valuation domains Z localized at 2, Z localized at 3, Z localized at 5, all work. All right, because it will survive in all of them. So why does this work? Well, as you know, I almost never play up the theorem so much unless there's a Zorn's lemon involved. So what we're going to do is, this is again, we got to build the Sagacious set here. I am going to consider the set of all pairs. Consider all pairs Ri, let's say Rj, Ij, where Rj is an overring, right? And Ij in Rj is a proper ideal. And I is contained in Ij. So what I'm going to do, starting with my given ideal I, that is proper ideal of R, I'm going to look at all pairs, Rj, Ij, where this is a ring containing R, this is an ideal of R that Rj is proper and contains the ideal I. And I am going to partially order this. Well, actually, I want you all to help me on this. We say Rj, Ij is less than or equal to Rk, Ik, if, what partial order do you suppose I should be thinking about right here? Okay, and the rings. I want both conditions. Now, you can notice that there's probably an enormous number of pairs, right? Because, in fact, you might have some situation where these are the same rings and these are different ideals that are not comparable, right? So this is really a partially ordered set. Let me call this something capital gamma. This is a collection of all pairs that have this partially ordered by, you got to contain them in both. In fact, you have to have the same containment in both pairs, right? Notice that so at least I can convince you that I'm not up here proving theorems about the empty set, right? This they did here. Now, you probably smell Zorn come along, and that's exactly it. What do we want to do? We want to prove that every chain has an upper bound here. So and let's call this set RJ, IJ. I'm using the notation of it, be a chain. In gamma. What do you suppose that we should? What should I pick for the upper bound? Let's pick, let's say T A, where T is the union. And A is the union of all the I out. J's. Okay, we've seen before that T is a ring, right? It's a union of a chain of rings, right? And A is an ideal of the union, right? Let me kind of talk you through this. Let's suppose A1 and A2 are in here. That means A1 and A2 are in some one of these IJs, which means that A1 plus A2 is some of the IJs, so it's in the union, right? Same deal, if you have A in here, it's in one of these, when you multiply by something, an R is still in there. This is a bona fide ideal, right? Notice that these are also proper, because none of them contain one, so the union can't contain one. Right, okay. TA is maximal element gamma. Or is upper bound. In gamma. Because T is a ring, A is a proper ideal of this, and clearly A contains I, because the union of a bunch of things contain I. Right? So what's the end game on this? By Zorn, I'm gonna change the name here. We obtain maximal of gamma, and I'll call it VJ. V is VJ is the maximal element, J contains all these ideals, and V is the union of all, or well, it's maximal ideal, contains all of them. There's nothing larger than this. So suppose C V is valuation domain. Let U be in the quotient. Right. We need to show that either U or U inverse lives in V. By previous, J must survive in VU or VU inverse. Right? Because J is a proper ideal of V and it must survive in one of these. But V is maximal. So V equals VU or V equals VU inverse. So U or U inverse is in V. So V is a valuation. And there you go. Okay, any questions on that? Okay, I'm sorry, I ran over 2 minutes. I apologize for that. Put that in your pipe and smoke it. Think about the